So, dear colleagues, welcome to our theoretical seminar. So today we have a guest from very far away country, from Brazil, University of Campinas, Mr. Jorge Fernandez Herrera. So he will tell us about his research done during his PhD on plasmonic sensing using prism and waveguide coupling. So I remind you the rules of the seminar. Should you have some questions, please either raise your hand and then you will have a chance to ask it by voice. You may also type the question in the chat. So if you ask by voice, please make sure not to interrupt the speaker just in the middle of the sentence. You will have chance to ask even during the talk. With that, George, please, you're welcome.
Thank you very much for your presence today. Okay, thank you for your presence in this seminar. My talk is about consideration on plasmonic sensing using prism and waveguide coupling. I am PhD candidate at University of Campinas, here in the Campina city. Campinas is a city inside the Sao Paulo state, here in Brazil, in the southwest of Brazil. And I work at the Laboratory of Computational and Applied Electromagnetics in LEMAC, in the School of Electrical and Computer Engineering at University of Campina. What is the motivation of my work? It's because in this period of our life, we realize that it's very important, the sensing and the biosensing, for example, to avoid some very bad situation like pandemics, like COVID pandemics, and we realize that it's very important, an early detection system to avoid a lot of deaths and in many disease situations. And inside, in the area of optical biosensing, in particular, and optical sensing, the plasmonic sensing is one of the most important tools to work with. And this tool allows us to work with real-time detection, early, very high sensitivity values, and it allows to work with biomolecular interaction studies, drug discovery and screening, kinetics and thermodynamics analysis, and many other applications. And it reflects in the market size of sulfide plasmon resonance. For example, we can see in this slide some values. In 2019, the market size of plasmonic sensor was about $500 million, and the projection for 2027, the market size will be more than $1 billion. So it's because there are many research groups around the world working in many aspects of plasmonic sensing, optical biosensing, in particular in plasmonic. For example, I group it in 4 lines that the different groups are working. For example, they are working in analysis structures to improve plasmonic resonance, some interesting new structures. Other research line is evaluation of impact of the microfabrication issues. Was the evaluation, for example, in adhesion layer, in titanium or chromium, and its impact in the quality of sensing. Other line, the first line, is better analytes for specific and reliable detection. This is part of biosensing part, biological aspects of the development, new aptamers, for example, or new analytes to improve the selectivity of the optical sensors. And last but not least is the development of lab-on-a-chip paradigms. So there are many groups that are working in the development of very teeny, very cheap platform, easy to use, and able to be used in rural areas for early detection. And this is lab-on-a-chip paradigm. So there are many groups that are working in this subject. So in this presentation, I will discuss more my contribution in the 2 first lines. Is analyze structure to improve plasmonic resonance and evaluation of impact of the microfabrication issues, in particular the adhesion layer. Okay, I divided my presentation in two parts. The first one is using prism, is the Kretschmann configuration, and the second part is using waveguide. This is the first part, and in this photo we can see that we are using a prism, and there are many other parts. For example, this is a gold layer. This is the photo detector, and it is the laser is coming in this point, and we can see that this red point is where the laser is impinging the surface, and we can see some microflective tubes. This is the Kretschmann configuration because we are working with angular interrogation system. What are the fundamentals of Kretschmann configuration? In Kretschmann configuration, we use a prism. We put a gold layer in contact with the prism, and over the gold layer, we put a sample layer. So we have an incident beam in this direction, and we can collect the reflected beam. So we can plot a curve with the relationship between the reflected beam versus the incident angle. For different angles, we can plot a specific value of the reflected beam, and we can find the resonance condition. The resonance condition is when the reflected beam is near to zero. In this case, using a wavelength of 632 nanometers, it means a red laser, and using a sensing medium of air and gold thickness of 48 nanometers, we can plot this curve. Okay, the resonance angle is very close to 42 degrees. And in this curve, we can identify some parameters to evaluate the quality of my resonance. For example, the extinction ratio and the width of my resonance curve. So in this case, it's the full width half minimum. It's more or less the width in where the minimum, the half minimum of the power. We can establish some distance in this position, and it means the width of my resonance. There are very important parameters of my to speak of the quality of my resonance. Okay, so it's the mean in this case we are using air, but for sensing application, it's more interesting to plot the resonance curve using water. In this case, for this wavelength using red laser in the visible domain, the refractive index of the water is around 1.3329. And we can see that the resonance angle will shift to more or less 72 degrees, is more or less the direction. And we can see that the width of my resonance increased too, so the resonance curve is wider. And we can use this resonance to change the refractive index of my sensing medium, and we can track the minimum, and we can calculate the variation of the resonance angle, and put in comparison with the variation of the refractive index of my medium, and we can calculate the sensitivity of my system. In this case, the variation of the resonance angle in relation with the variation of the refractive index of the sensing medium, and in this case, the sensitivity is 145 degrees per refractive index unit. Okay, this is a very important value. It's very popular in many articles, in many works. But in this particular case, we are interested in change the sensing medium to put not water, to put in this case ethanol fuel. The refractive index of ethanol is more or less 1.3638 in the visible range, and we can track again the variation of the resonance angle when we change the refractive index of the medium. But in this case, the sensitivity is around 200 degrees per refractive index unit. So what happened? Because the last slide is 145. So what is happening? It's expected, in fact, because the sensitivity vary according to the refractive index of the value. So it's very important to take account the situation, because the sensitivity is increasing as the refractive index of the sensing medium is increasing too. But
so, George, sorry for interrupting. So may I ask you a question? At which particular wavelength do you measure this sensitivity?
The particular wavelength is 632 nanometers. It's a red laser. We're using a red laser. Okay.
Good. So
visible.
helium.
Yeah. Good question. Okay. And but all these results are using simulation. Okay, theoretical results using the Fresnel equation at multi incident, and there are some equation for the Fresnel reflection coefficient.
Yeah, right. But then another question: how strong is the dependence of sensitivity on the wavelength? So if you change the wavelength to, let's say, 550 nanometers, do you expect?
Yes, the sensitivity shines with the wavelength. So, but in this case, we are fixed the wavelengths for practical reason. We are using one laser. And in all my presentation, I am using only red laser, only the same wavelengths.
Right, thanks.
Okay. In this part, I put attention in the curve, in the resonance curve, because when I vary the refractive index of my sensing medium, the sensitivity increase, okay, but the behavior of the curve will change too. For example, in this case, we have a very traditional curve, more or less. The resonance angle is near to 72 degrees, and we can a very high extension ratio. In the maximum and the minimum, there is a more or less important difference. But what happened when I increase the refractive index of my sensing medium, we can see that the resonance angle shift to bigger values of angle incident. It's more close to 90 degrees. So it will be more difficult to get a reflected beam because it's near to normal to tangential incidence. And we can see that the resonance is wider in this case, so it's bad for selectivity, for example. So it's more complicated. So for higher values of refractive index of the sensing medium, the resonance curve will be more complicated for practical reasons. In this particular case, I will work in these windows around 1.36 because my practical application is the detection of adulteration of ethanol. And ethanol is ethanol fuel is a liquid that we can use for fuel activities in cars and other application. And my practical application was in the evaluation of the adulteration of ethanol fuel. Okay, and the refractive index is around this value. Using but this curve was obtained using a gold thickness of 48 nanometers. 48 nanometers thickness of gold. Okay, but the sensitivity depends too on the gold thickness, and we can plot the sensitivity. For example, the sensitivity is using 48 nanometers is around 200 degrees per refractive index unit, but when we change the thickness of the gold layer, the sensitivity decrease or increase along with the thickness of the gold. So we can plot a new curve showing the sensitivity variation in function of the gold thickness of my gold layer, and we can see that the sensitivity increase together with the thickness of the gold in this sensing medium using 1.3638 to 1.365 of the variation refractive index. But again, the resonance curve will be different. So my work put special attention to the resonance curve because when we think in the plasmonic resonance, we think that in all situations it's the same curve. No, the resonance curve vary together the variation of the gold thickness of the variation of the sensing medium refractive index. So it's important to this is the contribution of this part. So using 30 nanometers gold thickness, we can see that the extinction rate is low. And using 80 nanometers of gold thickness, we can see that the extinction rate is very small and very small, and we can lose the resonance. In fact, because if our system has some noise level very high, we can lose the resonance and we can lose our information of detection. Okay, and it's very difficult to work in both regions. Okay, it's better to work in the central region in order to get a best resonant curve. But we can explore possibilities in this position, for example. Why? Because the sensitivity is bigger in this situation. Okay. In this part of my presentation, I will take account the other requirement for glass metallization. It is the adhesion layer. What is important? Why is important the adhesion layer? Is because when we deposit gold directly over glass, we have low adherence and loss of gold. We have low durability of gold layer, but we have better resonance Q factor. For example, in this photo, we can see the effect of when we have a very bad adhesion layer. In this case, we present a loss of gold, and obviously it is bad for reuse our slide. We want to reuse many times the same slide in order to avoid repeat the fabrication of the metallization of my glass slide. But it's important to use an adhesion layer. With adhesion layer, we get better adherence. We get a capability of reuse of slides, but the adhesion layer affects the plasmonic resonant quality. Okay, and we analyze this part in the next slide. But we can see in these photos the difference that when we don't use adhesion layer, we can lose the gold, and when we use a good adhesion layer, we maintain the loss in contact in the surface of my slide, and we can work with this sample. What is the impact in the resonance curve? This is the situation. Professor Andre raised his hand.
Yes, please, Jorge. Did you use a chromium layer for adhesion?
No. In my lab, we use only titanium. And according to the technical literature for optical application, is better a titanium layer for adhesion. There is other option, chromium, but chromium is according to literature I reviewed. The chromium is better for mechanical situation because the chromium has some diffusion inside the gold layer, and it's not good for plasmonic resonance, for example. But titanium, not diffusion inside the gold layer, and for optical resonance is a little the suggestion is to work in optical experiment with titanium better than in chromium.
Okay, I see. Thank you.
Okay, and this is the effect of the titanium adhesion layer in the plasmonic in the resonance curve. So it's a very big impact. And sometimes it's not discussed in some presentation, the effects of the titanium layer in the plasmonic resonance curve, and it's very important. For example, we can see the difference of the resonance curve without titanium layer. Okay, it's a very big extinction rate. The maximum with the minimum is very high value, and using titanium layer, the extinction rate is shorter. Okay. And the resonance curve is wider too, so the selectivity is impacted with the difference. More or less, the resonant angle is more or less the same, no problem. And this is the comparison between sensitivity with the gold thickness, no? Without titanium layer and using 5 nanometers of titanium layer. So more or less, the thickness of the adhesion layer is more or less 5 nanometers. 2 nanometers, 7 nanometers, is according to microfabrication capabilities of different laboratories, but it's in this range. Again, we pay attention what is the behavior of the resonance curve. In this case, using very thinner situation of gold thickness, we can see that we can capture the resonance, we can track the minimum of the resonance. Okay, using more or less 50 nanometers of gold thickness, we can get the traditional curve, resonance curve, for example. It's good to track the minimum. And again, for thicker values of gold thickness, the resonance condition, we can lose the resonance condition because the extinction rate is very low, is very small, and we can lose this resonance condition. In fact, for for thicker values of gold thickness, there is a non-resonant region because this resonance is lost for thicker values of gold.
So may I ask another question about this previous slide? So maybe can you give some qualitative reason why adding titanium, even very thin layer, significantly suppresses the extinction? Maybe I missed this part.
Okay, if we vary the thickness of titanium.
Yeah, right. So you see the big suppression.
A big suppression?
Yeah. So you had this extinction 80%, but now you go down to 40%, let's say, for 60 degrees of incidence angle. So what is the qualitative reason for that?
The difference with the titanium thickness.
Yes. So big difference between blue and orange curves.
Yeah.
Why is that?
The difference.
Yeah.
The difference in between blue and red curve. The difference in the extinction rate.
Yep.
We can see, for example, is the more or less 90 to 90 maximum, and minimum is near to 0. Is the extinction rate is 90% in blue, for example, blue curve.
Yeah.
And in red is 16 more or less to 5 more or less. So the extinction rate is more or less 55% of the intensity.
Right. Why this happens?
Why this what?
Happens.
Why this happens? Okay, it's because why this happens? It's because as you increase the adhesion layer, how can I say? Because the plasmonic excitation in the interface between gold and sensing medium is attenuated because we have to take account and bond layer, the intermediate layer, that is that adhesion layer. And this material damping is a process of damping of the resonance between the prism and the gold layer, because for plasmonic resonance, theoretically, it's not needed the titanium layer. It's only for practical issues. And the effect in the resonance, in the plasmonic resonance, the more we can say the evanescent field produced in the plasmonic polariton is reduced with the presence of the titanium layer. Okay, more or less this.
Yeah, right. Good. Thanks.
Am I right? It is just losses in titanium layer, just losses.
Exactly.
That's all.
Some losses in the titanium layer. Yeah. Thank you, Professor. Okay. Okay, we plot the heat map of the sensitivity according to the gold thickness and the titanium thickness. Okay, we obtain this heat map only with simulation. Okay, for different values of titanium thickness and the gold thickness from 0 to 20 nanometers of titanium thickness and 30 to 18 nanometers of titanium thickness. For example, for 10 nanometers of titanium thickness, we can see that for 65 nanometers of gold thickness, we enter in the non-resonant region because we lost the resonance condition. And we can see, according of this heat map, that the better condition is the better sensitivity values is for gold thickness more than 65 nanometers and using titanium thickness shorter than 3 nanometers of thickness. And we can, using this resonance curve, we can take account the second parameter, that is the width of my resonance, and we can plot the figure of merit too. The figure of merit is the relationship between sensitivity and the width of my resonance curve. And we obtain the second heat map that we produce is the figure of merit map. And we can see again that the higher values of figure of merit is for thicker values of gold and thinner values of the titanium layer. We produce this heat map using many simulations in this range using ethanol fuel sensing medium. This is our experimental setup. We used a red laser, a canyon laser is over here. We use some mirrors, an optical isolator, optical attenuator, and this is our theta double theta rotation system. We put our prism in the center of the system. We put our microfluidic system, our photodetector, and this rotation system was managed by Arduino controller, and the Arduino was managed for the human-machine interface developed using Python. This is a photo of my experimental of the optical table with the optical tools working. In this part, I presented a short video how my system is working. This is the tracking system interface. First, I configured the angular range, the angular position, initial position, final position. I put the name to save data, the name of the file. I put the number of runs, and I start the scan process. The number of runs is the number of runs that the photodetector and the system go and back in the start position. We can see that the system is rotation. This is the step model, and this is the theta double theta system. This is photodetector in this part, and we can see that the system is go and come back in the start position. And when achieve the start position, we generate other resonance point. In this system, we are tracking in real time what is the resonance point, and we can vary the refractive index of the media, and the resonance point will change. And in this means in this way we can capture the variation of the refractive index, seeing the variation of the resonance point. Okay, this is a short video of the system working. We use this system in the case of ethanol fuel adulteration. And the ethanol fuel has an interesting property because for low concentration of water, the refractive index of the ethanol increases. And for more percentage of water, the refractive index decreases, obviously. But in the very short range for low concentration, the refractive index increase, and we work in this part for low concentration of water in ethanol. For this, we use a refractometer method Toledo. This is these tools to measure the refractive index of the liquids. This is our pump to put the liquid inside the microfluidic pump, the microfluidic tubes to put in contact with gold. Okay, and we test many different slides with different gold thickness. For in this case, this is the first slide, and we can capture the minimum with the variation of the ethanol concentration, and we can get a slope. The slope of the line represent the variation of the angle shift versus the variation of refractive index. It means the sensitivity of my slide. This is the second slide. Using 50 nanometers of gold, we can get other slopes. It means other sensitivity value. And finally, using 75 nanometers, we can get other sensitivity value. We compile, we present these results in these tables. The experimental sensitivity is very close to the theoretical sensitivity. The relative error is very small. And the second table presents the experimental figure of merit in comparison compared to the theoretical figure of merit. The values are very similar, and the relative error is very low. What is the more or less the conclusion of this part is that if we have low noise level setups, it allows us to work with low extinction rate curves, and it means we can get higher sensitivities. And what is important, because the commercial setups with Kretschmann configuration all is working in 50 nanometers of gold layers. So with this work, we can show that we can use other thickness of gold in order to get better performances in our sensing. Okay. This is the second part of my presentation. In this part, I work using.
Jorge, I'm sorry. Can I ask a question before we went on? Yeah. So
if you have any question, yeah.
Yeah. So here, what about the quality of the interface? And depending, are there any studies, or did you provide any? You carry out any, like with different methods of evaporation, of sputtering of these thin films?
No. I only used an evaporator to get thin films of titanium and gold. Only an evaporator with very, very vacuum level, very high vacuum level.
Was it a heat evaporator or electron beam evaporator?
No, it's no electron beam. It was an evaporator and induction. I don't remember the names. Induction, high induction.
Okay, I got it. Based on
it's not electron beam. It's not sputtering. I think I was talking with other researchers, and I think that the sputtering, the deposition will be worse, will be more with more roughness, I think, in sputtering. But using an evaporator, we can get better condition for the uniformity of the deposition, I think.
Yeah, that was my second question. So,
okay,
was there any? What is the roughness, and how roughness affects the sensitivity? So, what was the roughness of the filament, if measured, and will it bring any additional disturbance in the results?
Okay, in roughness, according to I work with a technique that works in the deposition in the evaporator, and he said me that the roughness is lower than 2 nanometers in the surface. So, but I didn't simulate the impact of the roughness in my system. I didn't.
Yeah, but if you say that's 2 nanometers for 5 nanometer film, that's already so almost.
Yeah, but in fact, he said me lower than 2 nanometers, but for titanium gold and titanium layer, the thickness is in the order of 2 nanometers. But in this case, I think the roughness will be obviously lower than 1 nanometers or something like that. And in the case of gold layer, the thinner gold layer that we used was 35 nanometers. And I didn't work in the simulation, the modeling of the roughness.
Yeah, so probably something could be seen. So once you make very thin layers below this roughness, so your results could strongly deviate from the theory, and that could be one of the signs that the roughness is crucial. Okay, but I got your answer. Thank you.
But then, Jorge, a short follow-up question. So, what kind of effects do you expect at the qualitative level due to roughness? Do I understand correctly that it's just only the broadening of the resonance which happens due to roughness?
The roughness?
Yeah. So, what kind of effects it produces just at the qualitative level?
The quality of the resonance curve. No, this width.
No, yeah, I think Maxime asks what will happen if we introduce roughness, like
the simulation. Yeah.
What will happen if I introduce roughness in the simulation?
What do you expect?
I expect the variation roughness in my simulation. It could introduce variation in the gold thickness. So these curves are the same using theoretical situation, okay, perfect, no roughness situation. If we get some roughness, I expect that the resonance curve will be worse, more worse. It means reduction of the extinction rate and wider the resonance, the width will be bigger, so it's not good for resonance quality. This is like I expect, talking about the roughness.
Can you perform such kind of simulations? Because in fact, you need to include some statistical averaging over some random reflections on these imperfections. So do you have some tools to simulate this?
What tools I used?
No. So do you have some tools to simulate the sample with the roughness, or some techniques?
I didn't work with roughness.
So you just do not consider it at all. So
yes, I only simulated with no roughness, flat surface.
Right. Okay, thank you.
Okay. But in the future, we can take account this roughness, because there are some models to model the roughness in the surface, and could be interesting for next works. Thank you for the recommendation. Okay. Okay, this is the second part. In the second part, I worked with waveguide coupling, and we can see a ship with a drop of water in the middle, and we can see fiber optics with the light in the input and the output of the ship. Okay. In this part, I work with hybrid plasmonic waveguides. What's the idea of this kind of waveguide? I model it using a silica substrate, silicon nitride core, dielectric core, and over the silicon nitride we deposit on silica over cladding, and over the silica over cladding we put a gold layer. That gold layer can be biofunctionalized with biosensor application. And we have an input section, an output section, and in the gold deposition it is the sensor length. We can change the fluid in order to perform the sensing operation. And what is my work in this with this device? I perform the modal analysis of the hybrid modes in the sensing region, in the gold region, and we analyze the impact of the lower index material thickness, gold thickness, and the sensor length in the sensitivity. Okay. In fact, we published these results in this article, Plasmonic Sensor Design Using Gold and Silicon Nitride Waveguide, Visible and Near-Infrared Wavelengths. We published in this journal, Optics and Laser Technology. Okay, what I performed in this situation, we capture the monitor of the electric field propagation along the hybrid structure, and we can this is the resonance condition. So at in this part, I present the transmission. Okay, the transmission. In the transmission, we can see that we can capture the resonance condition. The resonance condition is in this case, is not angular interrogation system. In this case, it's wavelength interrogation system, and we can detect what is the wavelength where the resonance is produced, and we can see that for different length of the sensor of the gold, we can get different quality factor of the resonance curve. For example, using 5 micrometers is the red line. Using 8.5 micrometers is the red. So we can see that the extinction rate is lower and the resonance curve is bigger. And using 13 micrometers, the length is the yellow curve. So the resonance is deeper and more or less more thinner, more narrow. But how it works, because when we put a linear monitor in the center of the dielectric core, we can see that we can get some local minimum and local maximum. Okay, because in this hybrid region, is performed and beating modes. Okay, the hybrid modes is beating along the resonance region, and it's contribute to generate a local minimum and a local maximum. So, and it affects the quality of my resonance. And what is the impact in the sensing performance is that I analyze in this work. In particular, for practical reasons, I work with pedestal waveguides, because in this part we are in collaboration with a group of the University of Sao Paulo, and they are very good fabricating this kind of waveguide, pedestal waveguides, and we metallize some part, and we are working in collaboration with them. Okay, but the situation is the same. The situation is the same. We performed some simulation to evaluate the variation of the variation of the refractive index of the modes, of the dielectric modes in pedestal waveguide and rectangular waveguides, and their effective index are very similar. In this case, the core is not silicon nitride. In this case, is pentoxide of tantalum, and we are using silica as lower in this material between the core and the gold layer. Okay, it was identified the equivalent strip waveguide. Okay, for modeling, for simulation interest, it's easier to work in this platform. And we analyze the behavior of the hybrid modes according to the dimension of that we are working in the implementation. Okay.
But so, Jorge, just a question about this implementation. So where do you put the analyte which you investigate? On top of the gold layer?
The analyte, the biofunctionalization.
Yes.
Until now, we are only test the variation with water and alcohol without biofunctionalization process.
Yeah, but anyways, where do you put this water and alcohol? On gold or?
No, the biofunctionalization is over the gold layer. Okay, in this microfluidic chamber, we put some fluid that prepare the gold layer with some analytes, aptamers, or some samples, and but the biofunctionalization process lasts 2 hours, some hours. Okay, it's not very fast, the biofunctionalization process, and I biofunctionalize the surface of the gold. After the biofunctionalization, I can put my samples to identify, to perform the sensing.
But I'm just asking maybe a very naive question. So you put some fluid on top of this gold layer. This modifies the effective refractive index for some modes propagating in the waveguide. So, and then what do you measure in experiment?
What I measure the output.
So the output field?
The spectrum. I measure the spectrum. I capture the spectrum at the output. And I see what is the resonance wavelength. Okay.
And it is associated with the propagation. Good. Is it related to the propagation constant of the mode? Actually, this.
Yeah, because when I put an input with a very wide wavelength range, different wavelengths propagate in different ways, but each of these modes are present and refractive effective index. Okay.
Yes.
And
absolutely.
Different modes has different mode profiles, for example. And in resonance condition that I present in the next slide, the resonance condition, we can see that there's very high loss because the plasmonic resonance.
Yeah.
And this resonance will change when we change the sensing medium. This is what that we track. We track the variation of the resonant wavelengths. Good.
So plasmonic resonance governs losses, and losses affect the output.
Exactly.
Roughly.
Exactly.
Okay.
Thanks. Okay. I continue. So exactly this is what is happening. Okay, I think that there are a lot of information in this slide. We have the input. In the input, we put the TM dielectric mode, wide band source, because we are working in analyzing the spectrum. We need a very, very wide band. This is the output. In the output, we capture the TM dielectric mode, obviously, because we in the input we have a TM dielectric mode. But what happening in the gold length? The hybrid modes beating in this region, we have two modes, TM0 and TM1. The TM0 and TM1 are different modes. Okay, the TM0 is more close to the metallic surface. The TM1 is more close in the metallic, but part of the mode is inside the dielectric core. And we can see this is the mode profiles in 800 nanometers, okay? And using 15 nanometers of gold thickness, okay? And what is the transmission? The transmission is the spectrum that we capture at the output of the device. And this is the output. We can see that the transmission vary according to the refractive index of our medium in contact with the gold. If we have iron, the refractive index is close to 1.0. It's the blue line, but using water is 1.3329, is more or less the refractive index of water in visible region. It's the red curve. Okay, the resonance is better for water because this device is designing to work with aqueous samples. And biosensing, the starting point to work in biosensing is able to work with the refractive index of water, 1.3329. Okay, and what the resonance is produced? What is how the plasmonic resonance is produced? It's because we have to analyze the dispersion relation of the hybrid modes. This is the behavior of the modes. The blue line is the dielectric mode, okay? The dielectric mode in function of the wavelength. The red line represents the refractive index of the hybrid mode TM0, and the yellow line represents the hybrid mode of TM1 in part of the refractive index. So we can see that the input for shorter wavelengths, the dielectric mode fit the hybrid mode TM1. And this mode presents very low loss in this region. But for longer wavelengths, the dielectric mode is more close to hybrid mode TM0. So in this region, the TM0 present low loss. But in the center, more or less in the center region, the dielectric mode fit the TM0 and TM1 similar, and it presents very high losses. It's the plasmonic these losses are the losses of the plasmonic modes, and because that we have in this region very high losses because the plasmonic modes are propagating in this region, and it produces the resonance condition, and it's more or less the work principle of my device. And when we change the refractive index of the sensing medium, this behavior changed and the resonance point changed too. And it's that we track the variation of the sensing of the resonant wavelength when we vary the refractive index of the sensing medium. It is other heat map. Is the linear monitor along the waveguide. We can see that, for example, using shorter wavelengths, the propagation is no loss, practically no loss. In this case, using 660 nanometers, the mode is propagating along the dielectric core. But using a wavelength of close to 800 nanometers, we can see that the plasmonic mode is concentrated in the interface, and we lost the energy. We have very high loss. And using, for example, longer wavelengths, using, for example, 1000 nanometers, we can see that we produce some plasmonic resonance, but big part of the energy is propagating along the output of the devices, and we can plot. This is the resonance using the resonant wavelength, more or less close to 800 degrees. So it's similar to the previous one. Is, for example, this curve using water. So we can see that for shorter wavelengths, we have very high transmission. This is very high transmission. For 80 hundreds nanometers, we have very high loss, plasmonic loss. In this case is this loss. And for longer wavelengths using 1,000 nanometers, we have very high transmission. It's not so high like the 660 nanometers, but it's high transmission. Obviously, we can see this condition near to longer wavelengths. We have high transmission. In comparison with the resonance condition, is very high transmission. Okay, and we track the minimum, the resonance condition. Again, it was.
Jorge, I'm sorry.
Okay.
Sorry for interrupting again.
Yeah.
Can you turn on the previous slide? So some periodicity in the lower frequency at the
yes, in this part.
Lower wavelength is a Fabry-Perot kind of effect or what?
Interesting question. I think it's like a Fabry-Perot is because the reflection. I performed this simulation using numerical software, using the FDTD 2D solver. Okay.
So basically, what is shown is the transmission amplitude, right?
Yeah. The transmission amplitude is no, but the effect of this periodic reflect is a reflection effect, because with using shorter wavelengths, the structure can produce this effect, because the dimension, the structure, the waveguide was designed for very wide range of wavelengths, from shorter wavelengths until 1,000. So for shorter wavelengths, we can produce some reflections inside the structure.
Okay.
I have one more question, please. What did you use for these graphs? Did you use the Python or console?
Python? No, I used Numerical. It's a software.
Okay, thank you.
Numerical is an optical simulator software from ANSYS. ANSYS bought the Numerical, and it's more expensive now. But Numerical is a software to perform this kind of simulation. And I use MATLAB too. Numerical has an interface with MATLAB to post-processing the results. I think it's not possible to use Python with Numerical, but probably. But this main graph, these main results, I performed using Numerical. Okay.
Okay, thank you.
In this case, I performed only for simulation, only using Numerical, the variation of the refractive index of the sensing medium in the biosensing range. The biosensing range is a very small variation of the refractive index, for example, from 1.3229 to 1.3347. The technical literature for simulation in biosensing region, the variation of the refractive index is very small, and this range is used in these cases. And I changed the sensor length using 10 micrometers, 15 micrometers, 20 micrometers, 25 micrometers. And we can see that the resonance is deeper for this purple line, okay, using 25. And using, for example, a sensor length of 10 micrometers, the resonance is now so deeper. So the resonance curves for different God length values, this is the figure A, resonance curve for different God length. And the letter B is a resonance shift for different refractive index. So we can track the shift of the resonant wavelengths in order to get the sensitivity of my device. The simulation give us the next results. The sensitivity is around 450 nanometers per refractive index unit to around 500 nanometers. The figure of merit is around 7.6 to 15 per refractive index unit. And this is the simulation results using a silica thickness of 200 nanometers and gold thickness of 15 nanometers. And the next results is important to take account the titanium layer. Now, the titanium layer is important to take account, but in this simulation, we didn't take account the titanium layer. But for the next results, I will take on this adhesion layer.
So Jorge, sorry, we have like 4 minutes, just maybe to.
Okay. Okay, I finished. I finished it. This is the experimental setup. The experimental setup is the source, the optical attenuator. We have a polarizer because this super continuum laser is not polarizing, and we have to TM polarization. This is the polarizer. We use an objective lens to focus the light inside the waveguide. We use an spectrometer. In this case, it's a compact spectrometer, CCS 175M model Torraps. And we first capturing the source spectrum. This is the source spectrum of inside in my spectrometer. And in this case, I performed some tests using chips, using pedestal waveguides. And this is the chip, this is the fiber. We put the enter of the light inside the waveguide. We use some nanolight microscope to monitor in the optical alignment. The light enters to the waveguide from the objective lens. At the output, the light is collected by the multimode fiber. Okay, this is the multimode fiber. This is the light entering the waveguide, and we collect the output, the light at the output of the fiber. And it is some chips of pedestal waveguides with different widths. Only test chips. We will fabricate more chips for this specific application. Okay, but these chips are for general application. These many different conditions. Each waveguides are different. So this is a picture of the nanolight microscope. It's using a optical microscope. We can see that there is a deposition of gold, a very, very, very small deposition of gold. The length of this gold is 25 micrometers. Okay. And until now, we have some problems to detect the resonance condition. Probably the deposition is not so good, or the thickness. We have some problems to measure the thickness of the gold deposit over the chip. Probably it was measured in seconds. Okay, 3 seconds of titanium and 15 seconds of gold. We have to measure what is the thickness of the titanium and gold, but it's it's work in the laboratory of the University of Sao Paulo that we are working with. And this is the relation. More or less, we have some. We can see some resonance in this part, but we have to post-process the information to identify the resonance more clearly. And this is other chip using other waveguide, and we can see some resonance condition, but the results are not conclusive. We need more work to perform the correct identification of the resonance condition of the plasmonic condition and perform the sensing role in our chip. This is basically my presentation. Thank you very much for paying attention. I am open for questions. You can enter in contact with me with my email too.
Yeah, thanks a lot, Jorge. So I believe we had multiple questions during the talk. So if someone has some questions remaining, please, you're welcome.
Yeah, George, it's Pavel. Thank you for talk. It was very interesting. I have a question about the first part of the presentation. Could you please get back to the slides where we talk about the experimental setup there? Yeah, I mean the first part about the Kretschmann scheme. Yeah, okay. So I wonder what was the accuracy of the measuring of the angles here, because usually in these schemes the accuracy is quite low, and in my experience is not even comparable with the so what was the estimated accuracy, and
the accuracy, the angular accuracy is 0.015 degrees.
Could you repeat, please?
0.015 degrees is 15 micro degrees.
Oh, okay. And how do you achieve such a high level of accuracy? So if I catch it right, you used the Kretschmann scheme with quite a small radius of the rotation parts here. Like
how I achieve this high accuracy, because I use in fact 2 Arduinos. This picture was in the model. I only put one Arduino, but in fact I'm using two Arduinos because I am using synchronization and parallel working. One Arduino for the rotation system and other Arduino for the photodetector, because my system is as my system is rotating, my photodetector is capturing in real time in the same situation. But by that I can perform this video. Okay, you can see. Oh, it's not working. Oh, it's not working. But in the video, we can see that the rotation system is rotating, and the photodetector is detecting in real time all the intensities values. So we are not performing a step and rotation and capture, rotation and capture, rotation and capture. It's not because the resolution of my step model is not good. So we're rotating, and in real time we're capturing the intensity reflected. With this method, yeah.
Yeah. Okay. Thank you. I actually don't doubt the accuracy during the measurement, but my question is mostly about the adjustment of the step. So then you measure your angles. Yeah, you start from some kind of zero angles which you adjust when you build the whole setup, and usually these angles can be measured that accurate.
The accurate of the angles.
Yeah. So it will actually make quite a big influence on the whole picture of the resonance. So you have the center wavelength of the resonance, yeah, in absorption, yeah, on these graphs, yeah. But in case if you have any error in the initial adjustment on the zero angle, this
okay. No, but
can be.
Okay, but I understand that the angle position, for example, because in Kretschmann configuration,
just
the angle position, the resolution in angle position, because we are working only in it's a sensor working in comparison, so it's not important the absolute value. For example, absolute we track the initial condition using water. For example, we track this, and after we change my sample, and we measure the variation of the angle, not the absolute value. I don't know if it's useful.
Okay, thanks.
Right. So I suggest now, should people have some extra questions, they maybe can ask after this. So we have maybe to conclude now, and I have to go to the next meeting. Yeah. So look at the announcement of our website. See you soon. So goodbye.